Section 8.8 is called power series. This would be a good video to watch if you missed class on Friday, or also if you are interested in the very last example, or if you're confused on the homework, you might be interested in skipping just to watching example 1, all of it, or maybe just example 1, part C. So as a warm-up, I want to make sure that everybody has a quick way to solve absolute value inequality statements. So for example, part A, the absolute value of x minus 2 is less than 1. Now that you're calculus students, you might recognize the combination of absolute value and subtraction as the difference between two values. So you could really translate this as the difference between your solutions for x and positive 2 needs to be less than 1 unit. So a picture of this, you could put positive 2 as your central value. Go at most 1 unit away from 2 in either direction, and then shade the x values that live in that neighborhood. So if you look at my picture, I would have a description as to the solutions for x that would make the statement true. So it's just kind of a quick way to get inequalities with absolute value marks involved solved. So a similar situation could be the absolute value of x plus 3 is less than 1, in which case you could think of it as the absolute value of x minus negative 3 being less than 1. In this case, your central value would be negative 3. And you're looking for x values that are within 1 unit of negative 3. So for this problem, the solution set would be x values from negative 4 to negative 2. One more of these, and then we'll move on to something different. So if you have the absolute value of x minus 1 over 3, needs to be less than 1. In this case, I would recommend factoring the constant out from the absolute value marks. So in that case, you could think of this as 1/3 times the absolute value of x minus 1 needs to be less than 1. And then you could simply multiply both sides by 3, leaving you with the absolute value of x minus 1 is less than 3. And then from here, you have that magical combination of absolute value and subtraction. So your central value in this case would be positive 1, and you're looking for x values that are within 3 units of positive 1. So you could go up and down the number line. Oops. 3 units in each direction. And then think of the numbers that would be within 3 units of that positive 1 for a quick answer of any x value in the interval from negative 2 to 4. Okay, so now that we've reviewed how to solve those, let's move on. Oops, that was warm-up number 1. So warm-up number 2. Let's review what the ratio test is. Or what it says. So if you recall the ratio test, we're checking to see what the sum of all the a sub n's does. And we do that by testing the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. And based on what we get here, we can decide or determine what the sum of all the a sub n's was going to do. So if I say this is equal to some L value, then if that limit value is less than 1, then we would know that the sum of all the a sub n's converges. And not only that, but it converges absolutely. If that limit value right there is greater than 1, then we knew that the sum of all the a sub n's would diverge. And remember, and this is going to become key in this lesson, if your limit value is exactly 1, then who knows what the sum of all the a sub n's would do. So the a sub n's could converge or diverge. We don't really know. So the test is inconclusive if you got exactly 1. Okay, warm-up number 3, kind of a long warm-up, but we'll pull it all together to form the lesson here. So determine which x values make each geometric series converge. So for part A, let's give you the sum as n goes from 1 to infinity of x to the nth power. Okay, so if we think about this, I did give you a geometric series, and the idea is that geometric series will converge for only if your common ratio is in a certain range of values. So what's the common ratio for this sum? Common ratio in this case would be x, and you could expand it out to see that truth if necessary. So what do we need to have true in order for this to converge? This x value would need to have an absolute value of less than 1. So here we are, and we're kind of in the need to solve an absolute value mix with an inequality. And this is one I think that most of us would get pretty quickly. The answer is x values between -1 and 1. If you wanted to use the techniques that I demonstrated above, you could. It would look like this. You know, x is the same as x minus 0. And at that point, you're looking for the x values that are within 1 unit of 0, and then you'll get that answer that you thought it was anyway. So the answer in this case would be x values between -1 and 1 would cause this to result in a convergent sum. So part B, similar here. Another geometric series, so the sum as n goes from 1 to infinity of, let's give you x minus 1 over 3 to the nth power. Okay, so another geometric series, the common ratio this time is x minus 1 over 3. So if you're looking for it to converge, what type of common ratio would result in something here that converges? Well, we know that as long as your common ratio is less than 1, then you'll have something that converges. So here we are, and notice that this is exactly the warm-up that, whoops, am I pointing at the right thing? Yep, there it is. Exactly warm-up part C up here. So you would solve it similarly, maybe to the way we did it up there. So you'd end up with x values, any x value from -2 to +4. If you were to take anything from this set and put it in for x, you would end up with something, a geometric series that converges. So some vocabulary for you. These are called intervals of convergence. This lesson is going to be about finding intervals of convergence of series, whether they are geometric or not. And because we have to move past geometrics, we're going to employ the idea of the ratio test. And we're going to actually enforce the condition of convergence here for the ratio test. So what we're going to do is we'll probably rework maybe part B here, pretending it's not geometric. And so we'd need to do something beyond what we did there in the warm-up. And we will force this condition of convergence of the ratio test. And then we'll just solve for the x values that satisfy this condition, and those will be the x values that cause the sum to converge. Okay, so example 1. Use the ratio test to determine the interval of convergence and then they want you to state where each power series is centered and what's called its radius of convergence. Okay, so part A, let's reuse the geometric series that we used in the warm-up. We'll use the last geometric series that we used. So the sum as n goes from 1 to infinity of x minus 1 over 3 to the n. Now we already know the answer here. We already worked it out, and truth is if this shows up on your AP exam, I'm hoping that you really just do it the way we did here in part B, because what I'm about to show you is not easier. It's not super hard either, but this would be probably what we did in the warm-up is the most elegant solution to this problem. So let's pretend that either this isn't geometric or we didn't notice that it's geometric, in which case we would enforce the conditions. Let's say, where do I want this work to be? Let's say we enforce the condition of convergence of the ratio test. Okay, and is that sentence necessary? I say yes, because on the AP exam, they'll want you to be able to explain, and that little sentence takes care of a lot of that explanation piece. So I say practice it. So let's do that. So we're going to enforce this condition of convergence of the ratio test right here, where the limit as n approaches infinity of the absolute value of, so remember that inside the sum, you're going to see the definition of the nth term. So if this is the definition of a sub n, what would a sub n plus 1 be? It would be exactly this rule, just with any n in it replaced with n plus 1. So what would that be? That would be x minus 1 over 3 to the n divided by, to the n plus 1, and then divided by a sub n. So that would simply be x minus 1 over 3 to the nth power. And by enforcing the condition of convergence here, we're going to say that this has to be less than 1. Then the idea is if we can solve for the x values that make this limit statement be less than 1, we will have solved for the x values that will make this series converge, and not only converge, but converge absolutely. So once you're here, you just simply, cancel what you can or simplify however you can with or without sound effects. I go with. So, and then simplify the statement. So we have the limit as n goes to infinity of the absolute value of x minus 1 over 3 has to be less than 1. From here, you'll evaluate the limit statement, and the limit has n going to infinity of an expression that has no n values in it. So as far as this limit is concerned, this expression is a constant value. So what's the limit as n approaches infinity of the absolute value of x minus 1 over 3, you ask? Well, it's just the absolute value of x minus 1 over 3. And we're looking for that to be less than 1. So here we are solving an absolute value inequality statement. How can you do that? You could always factor this constant out front, multiply by 3. Yes, this is exactly the same thing that we had already solved earlier, but you do have a quick way to do it. Your central value would be 1. You're going to go up the number line 3 and down the number line 3 units, knowing that you're looking for values for x that are within that 3 units of 1. So at this point, we would say that your interval of convergence should include values from -2 to 4. And you and I know that from the warm-up that is the answer. But if you are using the ratio test then and not noticing that this is geometric, then you'll actually need to continue just a little bit. And what would that look like? Well, remember that the ratio test is inconclusive if that limit value was equal to 1. So if this limit statement that we've been working with, if that was exactly 1, then we really wouldn't know what the series would do. So when would this limit statement equal 1? It would equal 1 at the endpoints, at either -2 or 4. So if you're using a ratio test method, then the next thing that you will need to do is check what's called checking endpoints. So that would look like taking x equals -2, for example, and then going back up to the original series and just looking at, well, what if x was equal to -2? So if x was -2, we'd have -2 minus 1, which is -3, over 3, which is -1. So the sum, if x is -2, would be -1 to the n. And then you'll look at this sum and you'll ask yourself, does this look like this converges or diverges? And to me, this looks like a geometric with a common ratio that's -1, or you could expand it out and see. But either way, I'm hoping that you'll come to the conclusion that this diverges. So since it diverges, what that means is that in your answer for your interval of convergence, this bracket right here should stay a soft bracket. You should not include -2 as part of the interval of convergence. And then once you've checked -2, then you could check 4, the other endpoint of your interval here, and +4, and see what happens. So if you put 4 in for x, you'd have 4 minus 1, which is 3, over 3, which is 1, and that would result in the sum as n goes from 1 to infinity of +1 to the n, which also diverges. Which, surprise, surprise, we knew this anyway, but surprise, surprise, that would yield a soft bracket still for 4. So how do you answer this? They wanted to know what's the interval of convergence, and we have determined, again, that the interval of convergence would be from -2 to 4, not including -2 or 4. But then they asked where each power series is centered and its radius of convergence. So simply what that means is, where was this centered? So if you look at my picture here from -2 to 4, it was centered at 1. And then your radius of convergence would be your distance from your center to the outer edge here, which would basically be 3 units. So, and if you look at this little format here that we had right before we drew the number line, it should point out pretty quickly, pretty clearly where it's centered and what the radius of convergence is. So let's make it official. So the interval of convergence would be x values from -2 to 4. It is centered at x equals 1. And we usually use an uppercase R for a radius of convergence. Its radius convergence is 3. Okay. Same directions. Part B, this time it won't be geometric, so you would actually need to use the ratio test. That's how we do the sum as n goes from 0 to infinity of x minus 2 to the n plus 1 over quantity n plus 2 times 4 to the n plus 1. Okay, so again, in the spirit of being able to explain yourself on the AP exam, if you're finding the radius of convergence using the ratio test, you start out by explaining yourself just a little bit. So you've got this magical sentence. We enforce the condition of convergence of the ratio test. Okay, and let's get started on it. So we're going to take the limit as n approaches infinity of the absolute value of, first, a sub n plus 1. So remember, the rule you see in here is exactly for a sub n, and you're just going to take all the existing n's out, replace them with n plus 1, and then simplify with the rest. So if I take this n out right here, replace it with n plus 1, I'd have n plus 1 plus 1, which would be n plus 2. So x minus 2 stays the same. You'd have n plus 2 for your exponent. Notice the n here as well. Replace it with n plus 1. And so this factor would then say n plus 3. You're multiplying by 4. Replace that n with n plus 1. And your exponent would then say n plus 2. Now dividing by a sub n would result in a pretty tall fraction. So let's go ahead and just flip and multiply. So dividing by a sub n would be multiplying by the reciprocal of a sub n. There we go. And since we are enforcing the condition of convergence, we're going to force this to be less than 1. Next step, cancel as much as you possibly can. So I would say, for example, the 4 to the n plus 1 would cancel with all of the 4's down here except for one of them. The x minus 2 to the n plus 1 would cancel with all of the x minus 2's on the top except for one of them. From there, we'll write down what's left. So we'd have the limit as n approaches infinity of the absolute value of x minus 2 times n plus 2 over, what's left down here, n plus 3 times 4. And we're looking for the x values that would make this be less than 1. Okay, so next thing, I say factor out constant factors. So as far as the limit's concerned, n is the only variable. So we can factor out anything that, as far as the limit is concerned, is a constant factor. What would that be? I claim it would be the absolute value of x minus 2 over 4. And then still left inside the limit would be the absolute value of n plus 2 over n plus 3. We're looking for this to be less than 1. Next thing, evaluate the limit. This would equal 1. So what are we left with? We're left with solving for the x values that would cause this to be true. Factor out the 1/4. Multiply by 4. Translate. Distance between your solutions and positive 2 has to be within 4 units. So your interval of convergence should at least include numbers from -2 to 6. Now what? Let's check endpoints. And why are we checking endpoints? Because the ratio test is inconclusive when your limit value would have equaled 1, and it would have equaled 1 at either of these numbers. So let's check x equaling -2, for example. Go all the way back up to the original and see what happens if x is a -2. So we would have -2 minus 2, which would be -4 here. So the sum would have been -4 to the n plus 1 over n plus 2 times 4 to the n plus 1. Okay, so next thing, I like to replace that top piece with -1 to the n plus 1 times 4 to the n plus 1. So we could just cancel that out. And then look at what's left. You have an alternating series. What's the non-alternating part? It would be 1 over n plus 2. So if you use the alternating series test, you just need to make sure that 1 over n plus 2 approaches 0 as n goes to infinity, decreases in value as n increases, and is always positive. And if you can do that even in your head real quick, then you could determine that by the alternating series test, this thing converges. So what would that mean for your answer? It would mean that it's a subtle small thing, but it would mean your interval of convergence should actually include -2. So you would change that soft bracket to a hard bracket. And believe it or not, that's the difference between a correct answer and an incorrect answer for these types of problems. So if you check the other endpoint, x equaling 4, let's go ahead and double check that. If x is 4, then you'd have 4 minus 2, which would be 2. Oops, we're not checking 4. What are we checking? 6. Good. That was going to be confusing. Okay, so if x is 6, then you'd have 6 minus 2 up there, which is 4. Otherwise, everything else would be the same. Oops. And then these guys would cancel, and so you'd be left with the sum as n goes from 0 to infinity of 1 over n plus 2. Now you get to figure out, what does that do? Does that converge or diverge? If you do start expanding this thing, you'll notice that really it's just pretty much all of the harmonic series except the 1. And since the harmonic series diverged to infinity, I would say this is 1 less than that infinity, so I would say it diverges. Which means your interval of convergence should be exactly what you have here, hard bracket on the -2 and soft bracket on the 6. So where is it centered? Your number line should make that pretty clear, or your pre-number line statement should make it clear. It is centered at x equals 2. And what is your radius of convergence? So the distance from your center to either of the outer edges would be 4. And that could be clear from your picture, or again from your pre-picture inequality statement. This would be the answer for part B. Okay, part C, last one. Same directions, the sum as n goes from 0 to infinity of 3x to the n over n factorial. Okay, so what's the sentence? We enforce the condition of convergence of the ratio test. All right, now let's do it. The limit as n approaches infinity of the absolute value of, remember, go to the way they define the nth term and replace all the n's with n plus 1. Divide by a sub n, that's the same as multiplying by its reciprocal. Force it to be less than. If you're going to make this thing converge, it needs to be less than 1. Now let's solve for the x values that make this true. Cancel what you can. Rewrite your limit statement with what's left. So what's left in there? The absolute value of 3x over n plus 1. We're looking for that to be less than 1. Okay, so from here, let's factor out the constant factor. So as far as the limit's concerned, the absolute value of 3x is a constant. And what's left inside? 1 over n plus 1. All right, let's let n go to infinity on this piece right here. And what do we get? Yeah, 0. So what do we have? And I do recommend writing this part. We have the absolute value of 3x times 0 is supposed to be less than 1. And if you're not careful, this is going to leave you with a big head scratcher moment. Because isn't 0 always less than 1? And that's the exact point. There is absolutely no x value that could make this statement false. And I really like writing it with the x's there so it's as clear as possible. So I would say in this case that really x could be anything. So your interval of convergence would be all the way from negative infinity to infinity. I don't think there is a wrong answer to say where that is centered, but I think most people would say that this is centered at x equals 0. And what would we say the radius of convergence is? That's right, infinity. And what's nice about this answer is you don't have to check endpoints. All right, my friends. That's the basics of how to find interval of convergence using the ratio test. I hope this is helpful to you.